Measurement 2. Accurate measurement is the bedrock on which any empirical science must be founded. Concern about measurement accuracy is as old as human civilization and is even expressed in the holy texts of some of the great monotheistic religions. So far, we've considered informally some general ideas about measurement reliability and validity. It is, however, possible to treat some of these ideas in a slightly more formal way. One of the advantages of doing so is that it forces us to make explicit the assumptions we're willing to make about the measurement process. Bringing these out into the open should, amongst other things, enable us to explicitly consider whether they are reasonable. There are 4 parts to this lecture. In the first, I will set out the modest formalization of the measurement process known as classical measurement theory. In this context, I outline the idea of the reliability of a measure. After that, I move on to consider the implications of the simplest type of purely random measurement error in a regression model. In this section, I illustrate the key ideas with the results from a series of simulations. In the third part, I talk about the idea of scale construction, that is, the use of more than one indicator to measure a theoretical construct. Finally, I return to the idea of reliability and discuss how we can think about that in the context of multiple indicators. Some of the human sciences, most notably psychology, have a long tradition of taking measurement issues seriously. This has been formalized in what has come to be known as classical test theory. In this way of thinking about things, we have individuals who give responses to test items. In other words, they're going to be asked a question or asked to give some sort of response to a sensory stimulus, which could be verbal, visual, tactile, or whatever. The test is an instrument that is meant to measure a trait that is not itself directly observable, but is closely related to performance in the test. Think, for example, of an IQ test that measures cognitive ability, or a test that measures mastery of a foreign language, or the GRE, or a set of items that purport to measure introversion, extroversion, or whether you have an authoritarian personality. Consider just one item in the test. Let's assume that the answer given by an individual subject can be scored on a continuous scale. We will assume that this observed response is related to the underlying trait that we're interested in by a simple model. What we observe, in this case lowercase xi, is a function of a platonic true score, ti, which is not directly observed, plus some random measurement error. We also make some assumptions about the measurement error, which make this a particularly simple case to deal with. We assume that on average the measurement errors are centered on 0, and therefore cancel each other out. A fancier way to put that is to say that the expected value of the errors is equal to 0. We also assume that the covariance of the true scores and the error is 0. Another way of putting that is to say that if you knew an individual's true score, it would not help you to predict the sign or the magnitude in the error component of their observed score. Together, these assumptions imply that the expected value of the observed score is equal to the expected value of the true score. Given our assumptions, this is in no way surprising, but if we are confident that our assumptions approximate the facts of whatever we happen to be investigating, it does imply that measurement error per se is not necessarily a barrier to learning something from the data. So far, we've only thought about the average or mean score. What about variation in scores? We can think about this either in terms of variation in an individual's score on multiple occasions of testing, or, perhaps more naturally, given our concerns, in terms of the same test being given to multiple individuals drawn from a single population. The variance of the observed score can be written as the sum of three terms: the variance of the true score, the variance of the error, and twice the covariance of the true score and the error. But we have already assumed that the latter term is equal to 0, so we can remove it from the equation. It's now easy to define the correlation between the true score and the observed score. It is simply the ratio of the variance of the former to the variance of the latter. If there is no error variance, then there is a perfect correlation between the true score and the observed score. As the error variance increases, so the correlation decreases. By convention, we call the correlation between the true score and the observed score the reliability of a measurement. This is all very interesting, but not on its own terribly useful. We have defined what reliability is to mean, but given that one of the terms in the definition is unobserved, it's not obvious that we can learn much empirically about the reliability of our measurements. That would involve estimating some actual numerical values for their reliabilities. Is there a way in which we could do that? The answer is yes, as long as we have at least two observed measures of the underlying trait we are interested in, and we are prepared to make some more assumptions. Now, at this point, at least some of my audience will feel inclined to reject anything that relies on making assumptions. This, however, is a mistake. To make progress in any empirical investigation, we're going to have to make some assumptions. The search for assumptionless empirical results is self-defeating. We cannot literally pull ourselves up by our own bootstraps, and we are always going to have to assume something. That, of course, does not mean that we're completely free to assume anything that we find convenient. We all know the old joke about the economist stranded on a desert island with an ample supply of canned food, but no tools to open the cans with. He, because it always is a he, solves the problem in the following way. Let's begin by assuming a can opener. Well, nobody is advocating that. Assumptions have to be evaluated for their reasonableness on a case-by-case basis. In addition, it's necessary to appreciate that reasonableness is not a matter of literal truth. There are likely to be many assumptions that are not literally true or exactly correspond with the facts. What we want are assumptions that are simple and close enough to the truth for the purpose in hand. So, what assumptions are we going to make? If we have two measures of the construct we are interested in, then we're going to assume that the error variance of the first measure, let's call it E, is equal to the error variance of the second measure, E prime. In the jargon of classical measurement theory, this is often called, for reasons I failed to discover, or in fact actually investigate seriously, tau equivalence. It is a fact, ascertainable by consulting any introductory statistics text, that the correlation between any two measures can be defined as the ratio of their covariance to the product of their standard deviations. If we expand the covariance term in the numerator and then eliminate all of the terms that are assumed in our simple model to be equal to 0, then we can see that if our assumptions hold, the observed correlation is equivalent to our definition of reliability. In other words, true score variance divided by observed score variance. It follows trivially from that true score variance is the product of the observed score variance and the inter-item correlation. This has one important implication. Purely random measurement error will attenuate the observed correlation between variables. In other words, in a world where only random measurement errors impact on the measurement process, things will appear to be less related to each other than they actually are. That should be a bit concerning. But it also follows that if you know the reliability of a measure, which admittedly might be a big if, it is straightforward using fairly standard methods to correct for random measurement error. Let's now move on to the second section of the lecture. We're going to look a little more closely at the consequences of random measurement error. Consider two variables, y and x, drawn from a bivariate normal distribution where the means are equal to 0, the standard deviations are equal to 1, and the correlation is equal to 0.4. It follows trivially in this case that the predicted value for an individual observation, lowercase yi, will be equal to 0.4 times xi, plus a residual error ei. Let's call this the data generating model. It represents the real, but usually unobserved process that we're interested in. We're now going to play around with it and see what happens when we add random measurement error to the dependent variable y, and then to the explanatory variable x. In the first case, we add random error to y and define a new dependent variable y star, such that y star is equal to y plus e, where e is drawn from a normal distribution with mean of 0 and standard deviation of 1. You can think of this as simply taking our original measurement of y and contaminating it with some random noise in a way that mimics what might happen when we observe y and then attempt to describe the way in which it is related to x. It turns out that if we regress y star on x, then some things do not change. Most importantly, our estimate of the slope coefficient, in this case 0.4, remains the same as it did in the original data generating model. The take-home message is that adding purely random measurement error to the dependent variable y does not affect the estimate of the regression slope. So if that is what you are interested in, you have no need to worry. However, it does affect the residual variance, and consequently the correlation between y and x will be downwardly biased. This is perhaps a good point for a reminder that the slope in the regression and the correlation are quite different things. So, if we are only interested in the regression slope, we need not worry too much about random measurement error in the dependent variable. But what about random measurement error in the explanatory variable? This is quite a different matter. I create a new variable, x star, by adding random measurement error to x. If we regress y on x star, we can immediately see that the slope coefficient does not equal 0.4. In this case, it's only equal to 0.2. In general, random measurement error in x biases the slope coefficient towards 0. Now consider a slightly more complicated scenario. Instead of a simple bivariate regression, what happens if we have more than one predictor variable, and one of those predictors is contaminated with random measurement error? So in this setup, we will have two predictor variables, x and z, and only one of them, actually in this case the x variable, we're going to add to it some random measurement error. Again, we define a data generation model, this time by drawing three variables from a trivariate normal distribution. Y and x and y and z are correlated 0.4, and the two predictor variables x and z are correlated 0.2. This implies a regression equation for y in which both of the slopes are equal and take a value of 0.33. Now we create x star by adding random measurement error to x. Then we regress y on both x star and z. In this setup, we have one explanatory variable that's contaminated with measurement error and another that is not. So what happens? Adding random measurement error to x biases its slope coefficient downwards towards 0, and in addition, it drives the slope coefficient for z away from its true conditional value towards its marginal value. In other words, away from 0.33 towards 0.4. So, even if just one of the explanatory variables is contaminated with random measurement error, it has consequences for the estimated slope of all of the others. In this figure, we can see how things develop as we gradually increase the amount of random error variance in x, which is plotted on the horizontal axis of the figure. What we are plotting are the regression slopes for x, beta subscript 1, and z, beta subscript 2, for two scenarios. One in which the correlation between x and z is, as in the previous slide, equal to 0.2, and the second where we assume the correlation is equal to 0.5. At the y-axis, we see that under both scenarios, the two slopes are equal. But as the amount of random error in x increases, the two slopes grow apart quite rapidly, with the slope for the error-contaminated x converging on 0, and the slope for the uncontaminated z converging on its marginal value, in this case 0.4. Though all this may seem a little involved, these are actually very simple cases, and are probably quite untypical of what one might encounter in any realistic situation. Usually, we will have to contend not just with random measurement error in all of our measured variables, but also important sources of non-random error measurement in some of them. In these situations, unlike the simple scenarios we've considered here, it is not straightforward to predict what the consequences are likely to be, and a proper consideration of the issues involved would take us beyond the level of detail appropriate for an introductory course like this. What you can take away, though, is that measurement error issues are endemic to the empirical social sciences, have the potential to seriously mislead us, and should definitely not be swept under the carpet. If you feel you want to know more than what you have got from this particular lecture about these issues, then you are going to have to consult the relevant technical literature.